first thing we have to understand about gas walls and pressure is that there is two pressures at work here. Let's consider the syringe that we use for Boyle's law experiment. If we have it in the equilibrium position, we have a pressure inside. That's the pressure from the air molecules trapped in here. And we have a pressure outside, that's the barometric pressure. And then when they are equalized, the volume stops changing. If you compress the sample, there is a force now, there is a force built up. So that's called a gauge pressure increase. And then that restoring force makes the gas go back to the equilibrium volume. So as you can see, there is two pressures at work. One of them is called the gauge pressure, named after the gauge. So that's a gauge. And the gauge is reading 0 pounds per square inch. That doesn't mean the pressure is 0 pounds per square inch. It's the gauge pressure that is 0 pounds of pressure per square inch. The barometric pressure is named after the barometer. So this is something similar to a barometer. It's not exactly a barometer. There is a force keeping the liquid out there. Okay? As soon as you lift it out of the liquid, the force is gone. The liquid is not going to stay up there anymore. So that's pretty much how a barometer works. It's just that the barometer, instead of this liquid, has mercury. So let's get this out of the way. We are going to first talk about the gauge pressure, the origin of gauge pressure. So the gauge pressure is the internal pressure. Internal pressure, we are going to call it gauge pressure. After the gauge, and the way this pressure is generated is the molecules press against the walls of the container. So let's consider here a wall of a container, and then this container has 3 dimensions, of course, 3-dimensional container. And then there is a molecule moving, and we start by considering only one direction of motion here. So that will be the x direction going that way. So the molecule is moving in the x direction. The molecule has a mass. And of course, the molecule must have a mass and an acceleration in order to have a force, because this is the definition of pressure. So we have the pressure is equal to a force per unit area. So let's see where that force comes from in there. So we have a molecule moving, and then there is a number of them, so that will be n times m. So that will be the mass of a number of molecules moving. And then it needs to have an acceleration, and this is an acceleration in the x direction. To get the acceleration in the x direction, what you need to do is just write that this molecule has a velocity, a square of the velocity, divided by the length of the container. If you check dimensional analysis, just put those units together, and you will notice that the velocity is squared over an L. Let's suppose this is meters per second. A velocity is squared divided by meter, and what you get is meters per second squared, which is the units for acceleration. Then we make a little modification here. So the x, the y, and the z direction motion are all equally probable. That means that this b squared over L now becomes b squared over 3L. Now that we don't have an x direction, all the directions are equally probable, so that's what this expression becomes. And we still have the number of molecules with certain mass each moving in that direction. So now we have the expression for the force. Okay, so that would be a force. That would be a force. But then we need force per unit area to know that this is really where the pressure, the internal pressure that those molecules are exerting on the container comes from. So we add here to the expression, we take everything out there and we write an expression for the pressure. So the pressure is going to be equal to a force per unit area. We take the expression for the force, which is the number of molecules times the mass, is square root of the velocity, divided by 3L. But now we have an area here, so we have the area then, divide. And now we have here what is called the internal pressure. We have an expression for the internal pressure. That doesn't look too familiar at the moment, but you could rewrite that expression in such a way that looks like something you have seen before. So let's do that. Let's take this n here, and let's take this part 2. We can do even better. Instead of this LA, this is a length times an area. We can write length times area as a volume. Okay, so let's write here a note. Length times area. That means a length times an area is equal to a volume. So that would be the volume. And then we have here the m alone with the b squared. And we can do even better than that. But if we multiply this by 2, so we can divide this by 2. And there you have it. What we have here is that the pressure is proportional to kinetic energy. We have that the pressure, the internal pressure that the molecules generate, is proportional to their kinetic energy. Okay, so a snapshot of that, figure in as you need, and let's move on. So now we have what is the internal pressure, or the gauge pressure. When we do an experiment, we have two pressures at work. We already established that. We have this internal pressure, and then we have an internal pressure, which is called the barometric pressure, named after the barometer. So let's see what that barometric pressure is. So now we have the barometric pressure. So the barometric pressure, named after the barometer, and this is how we obtain a barometric pressure. Let's suppose you have here a column of air. So we're going to draw here a little column of air. And And the column of air has an area, a cross-sectional area, and it has a height. So what we do is we consider that the column of air, the base is at sea level. So this is sea level. And this area is exactly 1 meter square. So the cross-sectional area of that column is 1 meter square. The column of air starts at sea level and goes as high as the atmosphere gets, right? So that's into space, where the atmosphere ends finally. So as you can see, we have a column of air, and that air has a mass. So the air has a mass. So we have an air has a mass, and then is influenced by gravity. So the air has a mass, and then this mass of air is then influenced by gravity. So what we have is m times g. This is the acceleration due to gravity, because the air is under the influence of gravity. And that is equal to a force. So now we have where the force comes from. Now, because this force is acting on an area that is 1 meter square, right? So we take that. We get this pressure here. So what's the magnitude of that pressure? Well, according to estimates, this column of air weighs about, let's give it 10,300 kilograms. So the air on that column weighs about 10,300 kilograms. So let's put that together. We have, for the pressure, we have 10,300 kilograms. That will be the mass. Acceleration due to gravity, 9.8 meters per second square. And then we take that divided by the 1 meter square area. And what we get from that is equal to 101,325 newtons per meter square. You remember this kilograms times acceleration, mass times acceleration gives you a force, and the SI unit of force is a Newton. So we get a Newton per meter square. And we can label this as Pascal. So the barometric pressure in a standard SI unit is derived from those 10,300 kilograms under the influence of 9.8 meters per second square gravity acceleration over the area axis of 1 meter square, and we get 101,325 newtons per meter square, and that is the SI unit of pressure, and we call it the Pascal. But then we normally do not find the Pascal in the ideal gas law. What we find is 1 atmosphere. So that is equivalent to 1 standard atmosphere. So if you wanted to convert the units, you will need, let's suppose you have a Pascal quantity, some number of Pascal. Then to convert, you will need the 1 atmosphere is equivalent to 101,325 pascals. And then you will get your answer here. In standard atmospheres, which is the unit that is normally used for the ideal gas flow equation. So when you talk about gas flows, normally you will be wanting to convert whatever standard units of pressure you get into those atmospheres. Okay, so snapshot. Okay, so you have the information you need. Let's move on. So this is the pressure in pascals, and that's the SI unit of pressure. But then when we did an experiment on Boyle's law, and we wanted to use pounds because that's what we had available. We want to use some pounds of mass within 100 kilograms. And as a result, what we need is we need to use the imperial system of pressure. So let's move on to that. So the imperial system of pressure. Imperial unit of pressure. So what we have to do is we have to do exactly the same thing we did with SI units. We need a mass, we need an acceleration, and that is going to give us a force. And if we take that force per unit area, that is going to give us a pressure. So first, let's write the imperial unit of mass. So the imperial unit of mass is a slug. So 1 slug is an imperial unit of mass. And then we have to obtain the acceleration due to gravity in imperial units. That will be in feet per second squared. So we write here the acceleration due to gravity in imperial units, and that is 32. Let's leave it at 2 digits. Feet per second squared. So that will give us a force. And the imperial unit of force is the pound of force. So what we get here is that 1 slug exerts 32 pounds of force. And we should try to note here that 1 slug, 32 pounds of force. So that's the definition. 1 slug exerts 32 pounds of force at G is equal to 32 feet per second squared. So 1 slug is going to exert 32 pounds of force anywhere else in the universe. It only exerts 32 pounds of force under the Earth's gravitational field. So if we take a fraction of that, 1 pound of mass. So this is the definition that if you take part of this log, 1/32 of a slug, that would be 1 pound of mass, exerts 1 pound of force at G equals 32 feet per square. So that's how we get the imperial units of pressure. We got the imperial unit of mass, 1 slug. We get the acceleration due to gravity in imperial units. And when we put them together, we get the force exerted by 1 slug, 32 pounds of force in the Earth's surface. If we take a fraction of the slug, 1/32, we get what is called 1 pound of mass. 1 pound of mass exerts 1 pound of force in the Earth's gravitational field. So when G is equal to that number, that's the acceleration due to gravity, then 1 pound of mass will exert 1 pound of force. That's how we got the imperial unit of pressure, and that's what we're going to use. Remember, we use some cans. So we use some cans, and they weighted like a little bit more than 1 pound. So if this was exactly 1 pound, it would exert 1 pound of force for the Earth's gravitational field. Because it's 1 pound and 1/2 ounce, it exerts a little bit more than 1 pound of force. Now what we need is an area. The imperial unit doesn't follow a fixed pattern like the SI system. So the area that we use is inches squared. So we got area in the imperial unit will be a square inch. So when we put that together, we get pounds of force divided by a square inch. And finally, we get the imperial unit of pressure is pounds of force per square inch. We label as PSI. And you saw that before. You saw the PSI written on the gauge. It has PSI and it may also have kilopascal sometimes. The Pascal is a very small unit, so that's what we use. Okay, so I guess everybody has that. Let's move on. So now we know what we're going to use for Boyle's law. We are going to use the imperial unit of pressure, called pounds of force per square inch. What we need now is we have the pounds. We weighted the pounds on a scale, and then we measure the diameter of the plunger. So let's do that again. So we got the syringe, we will apply some force, and what we need to know in order to be able to do the entire calculation set is we have to know the bore diameter to compute the bore area. That means the area that the force is acting on. And from our results, what we got was that the diameter was equal to 9 9/16 of an inch. So we got a diameter of 9/16 of an inch. What we need to do is we need to get an area from that so that we can use the pounds of those sardine cans per the unit area of that plunger to get a pounds per square inch of pressure for that law. So let's do that. Now we get the area is equal to the square of the diameter over 4 times pi. So what we do 9/16 of an inch square. And we get 0.316. Now you can see that 0.316. So this is 0.316 over 4 times pi. And we get 0.249. We could round it off to like 0.25, and yeah, that would be more reasonable. So we got 0.2485. 2.5. That would be square inches. And when we are doing the calculation, we could round it off. You can say this is a 0.25 inches square approximately. Okay, let's move on. Now let's compute the two pressures, pressure 1 and pressure 2. Remember, there is actually 3 pressures, right? So we'll break pressure 1 first so we don't get confused. Pressure 1. So the pressure 1 was when there was nothing acting on that plunger. The pressure 1 was 0 gauge pressure, and the only pressure acting on the plunger was the barometric pressure. So we got that the pressure 1 is equal to 0 gauge pressure plus barometric pressure. So the pressure 1 was 14.7 pounds of force per square inch. So that's the barometric pressure in pounds of force per square inch is 14.7. And that was the pressure at the beginning. Now let's take a look at the second pressure. So for the second pressure, what we got is we have some gauge pressure plus the barometric pressure. So this is what the gauge pressure was. We had 1 pound and 0.5 ounces. So the first thing is to convert that into pounds completely. So we got the 0.5 this will be 1 plus 0.5 over 16 pounds, right? So remember that there is 16 ounces in 1 pound, and we have only half an ounce there. So that will give us 1.031. 1.031 pounds. So we take that 1.031 pounds and then we convert them, right? So this is pound of mass and is equal to pounds of force. It's equal to pounds of force because we're still doing the experiment on the surface of the Earth. So we can relabel this as a pound of, and then we divide by the surface area of that plunger, which is 0.25 square inches. And we get 4.125. There you can see that. So we got 4.125 pounds of force per square inch plus 14.7 pounds of force per square inch as the pressure number 2. So we had 18 point, let's round it off to 18.83. So put this together and we get 18.83 pounds of force per square inch. Now let's work on the pressure number 3. So for the pressure number 3, we added another can of sardines, and now the mass of the combined 2 cans of sardines was 2 pounds, 2.3 ounces. So we write it here as 2 pounds, 2.3 over 16. Remember, 16 ounces, 1 pound, so 2.3 ounces is 2.3 over 16 pounds. 2.3 over 16. And we get 2.1, 2.144. 2.144. What do we make this? 2.144. 2.144, and those are pounds of. Remember this, we are relabeling it. So in here we have pounds of mass, but then because of the definition, we can claim that these are pound of force now. Now we just put this together with the area of the plunger. .25 square inches. And we get 8.579, 8.58. Let's say it's 8.58. Let's write it as 8.575 here, and then that's PSI. And we add it up and we round it off. So we get 23.28. So the pressure number 2, we take that plus 14.7 pounds of force per square inch, and we get 23.78. 23.78 pound of force per square inch. So these are the numbers that we are going to need for Boyle's law. We need that pressure. We need this pressure here. And we need that pressure. Those are the 3 pressures we have to work with. And then we have 3 volumes and 3 pressures now. So I guess everybody has their notes. Let me just, I guess we got it. I will just write here the numbers again. So we have 18.83 and 23.78, and we have to match them with the volumes that we measure from the syringe. And the syringe volume was 8.75 milliliters and 7.10 milliliters, and that had contracted from 11.25 milliliters when the pressure was barometric, 14.7 pounds per square inch. Okay, now we are ready to do, Charles, these calculations. So what we're going to do, our approach will be, we're going to compute the volume based on Boyle's law, and then we are going to compare it with the volumes that we got. So we're going to write them up here. Volume 1 is equal to 11.25 milliliters. Volume 2 is equal to 8.75 milliliters, and volume 3 is equal to 7.10 milliliters. Now we take those numbers and we are going to compare and see if our predictions are correct. So to do that, we first find Boyle's law. Boyle's law says that the pressure times the volume is equal to a constant, which means that if you take pressure number 1 and 2, that will be equal to the pressure number 2, volume number 2, and will be equal to the pressure number 3, volume number 3. So the pressure and volume product is equal to a constant. And then we can flip this equation to solve for the unknown volume. So let's try for the unknown volume first. So let's try to find the volume 2 based on the data that we have, which is the pressure and the volume number 1. So we have here the pressure number 1, volume number 1 is equal to pressure number 2, volume number 2. So in order to solve for volume number 2, what we do is we take the pressure number 1 over pressure 2 times the volume 1, and that will be equal to the volume 2. This is how close that is to the 8.75 milliliters that we got. So let's just substitute here for pressures 1 and 2. So pressure 1 was barometric, 14.7 pounds per square inch. Pressure number 2 was after we added 1 can of tuna, and that was 18.83. 18.83 pounds of force per square inch. And the volume number 1 was 11.25 milliliters. So we take the pressure, 14.7 over 8.83 times the volume number 1, we get an answer that is very close to that. It's not exact, but it's 8.78. So you have to compare that with 8.75. Okay. Now we can take this same equation and try it out with the third set of data. So what we do is we're going to take the pressure number 1 or pressure 3 times the volume number 1, and that has to be equal to the volume number 3. We're going to see if they are equal. So pressure number 1 is 14.7 pounds of force per square inch, and the third pressure was 23.78 pounds of force per square inch, and the volume is 11.25 milliliters. Let's see what we get. 14.7 over 23.78 times 11.25, and 14.7 okay, we got like 6.95, almost 7. It's not that accurate, but it's good enough. So we got 6.95. So the one is a little further away from 7.10. So that was a little bit off. Uh, that is Boyle's law. So now we move to Charles' law. Guess everyone has the notes they need. So for Charles' law, we take another two parameters. Remember that when we are talking about these parameters, they belong to something called the ideal gas law. We're going to write that in a moment, the ideal gas law. But this is just to give you some kind of historical context. You know, these laws were discovered one by one over a period of a long time, and then they were put together into what we know today for gases in general. So let's move on to Charles' law. Charles' law says this. So Charles' law. Charles' law states that if you take the volume divided by the temperature, that is equal to a constant. That implies that if you take that volume and you relabel it, volume 1, temperature 1, 1, and 1, then that will be equal to volume 2, temperature 2, and that will be equal to volume 3, temperature 3, and so on. So this kind of follows the same pattern as Boyle's law, but in here we take temperature and volume instead. And then we find that the volume over the temperature is equal to a constant. So let's take the number that we got and see if it's true. For Charles' law, we got volume at a high temperature and volume at a low temperature. So the high temperature was 95 Celsius degree. So you take the Celsius degree and add 273 every time you want to convert it to the Kelvin temperature. So Charles' law must be in the Kelvin temperature in order for you to be able to use it. Remember. So the volume can be any unit. So this volume can be any unit. But this temperature has to be Kelvin. Unlike Boyle's law, we could have used any pressure and volume units we wanted as long as the units were consistent. So let's try what we got. We got volume 1. We are going to take it as being the low temperature volume. So that will be the complete volume, which is 157.5. And that was the volume of the container that we use and the tubing put together. So that was the volume of 157.5. Then some liquid went in when the temperature dropped. So that's what we have to subtract here. 41 milliliters of water that went in. And that gives us the volume at the low temperature setting. So we have 157.5 minus 41 milliliters, and we get 116.5. 116.5 milliliters. That would be the volume, and that's the volume at 0 degrees Celsius, which is 273 Kelvin. Okay, let's write it like that. Now we put the volume and the temperature together and see if the volume and the temperature um, ratio is a constant. So we are here the volume number 1 over the temperature number 1. That would be 116.5 milliliters over 273 Kelvin. And we get 0.4267. It's like 0.27. So that is 0.427, sorry. And this is in milliliters per degree Kelvin. We can write in degree Kelvin, or just Kelvin. Now we take the second step of the volume 2 and temperature 2. So the volume to be the full volume of the container, because nothing is used by anything by air. So we have 157.5 milliliters, and the temperature will be 95. So you always write 95 plus 273 to get the Kelvin temperature. And now we do the calculation. 157.5 over 368 degrees. We get a number that is kind of similar. It's not exactly the same, but it's within the range. 0.428. And this is also in milliliters per degree Kelvin. Now the thing here is that we could have been able to obtain the volume. We could take this volume here, for example, number 1, and predict what volume number 2 will be. Or take volume number 2 and predict what volume number 1 will be if we use this constant here. So remember, this has units, and this is the way you have to use it. If you want to cancel the degrees Kelvin, the Kelvins go here. If you want to cancel the volume has to go here. So let's write that again. We're going to predict the volume number 1 from the data number 2. So we have volume number 2 over temperature number 2 is equal to volume number 1 over temperature number 1. And that is equal to a constant. We're going to use this constant here. 0.428, and this is in milliliters per Kelvin. Okay. So now the volume number 1 is the one that we don't know. We want to predict it, but we know what the temperature number 1 is. We take the temperature number 1 as being 273 Kelvin. So we take the constant here, and we take the 273 Kelvins as being the temperature that we know. So this is for every 1 degree Kelvin, and that will cancel. and then the answer that you will get will be in milliliters. Mm. And you will almost answer. It's 116.8. Which is comparable to what you got here. So that's how you use Charles' law. That was simple. Let's look at another aspect of these gas laws. Okay, hope everybody got the data that they need from the board. Sorry, I had to erase it so fast this time. So let's look at another discovery of Charles. Okay, so this is not the only thing that he did with this law. Something else that he did is probably he did this, right? So we're going to draw a line here. And we're going to take this as being the volume. So that's like volumes here. That's 20, 50, 100, 110, and 20. So your volume is around here, the one that you got. That will be your volume at this temperature, and we're going to call this 0 degrees Celsius, like Kelvin. Because Charles originally did the experiment, they did not have the concept of a Kelvin degree yet. And we are guessing that he probably did this. So he set up his temperatures and his volumes. Now this will be around 100, 200, that will be 100, that's around 200, and this will be around 300 negative temperatures. So what he noted was, okay, in here we have 116. That will be 30, 40, 50, around here. And here he has his next volume, and that volume corresponds to 95 degrees in the Celsius scale. So we take this 95 degrees. And that's probably the kind of data that he got. After that, he proceeded to draw a line through the points. Okay, we draw a line through the points. And he noted that if you draw a line through the points, so this is the volume. He said, okay, yes, the volume goes to 0, the temperature reaches a certain number, and that number is always the same no matter what gas he was working with. And that happens to be absolute 0. So he discovered the volume will go to 0, that's a theoretical volume, at 273 Celsius below 0. So at negative 273 Celsius, the volume will go to 0. And very important to remember that the volume he's talking about is not the real volume of the gas. We're going to talk about that in a moment because we have an ideal gas law. So we have PV equals nRT. So that is the ideal gas law. That's all the gas laws put together generate the ideal gas law. And now he was saying that this volume will go to zero. So goes to zero. And the answer is, well, it depends on what volume means. Because there is another equation. This is not the only equation. This is the ideal equation. And there is a van der Waals equation. In the van der Waals equation, we have a pressure plus some correction that is like a square of concentration times some constant. And then the volume is also corrected. So what we have here, this is called the van der Waals equation, and it's saying the volume that we consider a volume is not the real volume. Because normally, in the kinetic molecular theory, we're saying that this is the container, and the molecules are so tiny that the volume is ignored. So if that volume is ignored, when all these molecules stop moving, the volume, yes, it will go to zero, the volume that we define as the volume in the ideal gas law. But then, when the molecular motion stops, what you will have is a tiny volume here. Everything will condense into a tiny amount. And then the volume is not really going to go to zero. The ideal gas law volume goes to zero because the ideal gas law volume is made of pure kinetic energy of the molecules. The molecules generate the volume by moving around. But if you make the correction with the van der Waals equation, there is a small volume that never disappears. So what Charles meant when he said that the volume will go to zero, he meant the volume, this volume here, will go to zero. Okay, this goes to zero, and this does not go to zero. Okay, so that's just like a side note. Now we move on to the ideal gas law because Avogadro's law is easier to understand if you have the entire ideal gas law written down. So let's write this. So for Avogadro's law, we would like to introduce something called the partial pressure. And we're going to just do a little example so you can get an idea of what the partial pressure is. So what we have is this. Let's suppose you have a container. And then on that container you have a few molecules. And we're going to say that some molecules are blue. 1, 2, 3 blue. Some molecules are red. 1, 2, 3, and 4. So according to the kinetic molecular theory, the molecules are also so small that they don't feel each other. Each molecule is independent of the other and they do not interact considerably. So what we have here is number of molecules. 1, 2, 3, 4, 5, 6, 7 total. So let's say the red molecules. red molecules, we have 4 out of 7. And blue, we have 3, 1, 2, 3. We have 3 out of 7. So if I give you a very simple number, let's suppose I tell you that the pressure, the total pressure is 760 millimeters of mercury. And this is also called torr. Find the pressure of blue and red. And we call that a partial pressure. So we want them separated. We want to know what the partial pressure is for each of them. And we know that the total pressure is 760 torr. So that's a very simple thing to do because of how we define the molecular interaction. So what we have is that for red, we have 4 over 7 of the red. So 7 is the total, and 4 is the part that is red. And this fraction of molecules is going to be also the fraction of the pressure. Same goes for the blue. You have 3 out of 7 blues. So the partial pressure is going to be that fraction, like the total pressure. Now this seems very oversimplified, but that's the way things work. So we have 4 over 7 times 760 torr, and we get 434 torr here. So the partial pressure of red is 434 torr. And the partial pressure of blue would be the other fraction, which is 3 over 7 times 760 torr, 326 torr. So let's label it correctly. The partial pressure of blue is equal to 326 torr. Let's suppose you don't want it written in torr. You want to write it in atmospheres. All you do is you take the 434 torr and use the conversion of 760 torr is 1 standard atmosphere. And we get 0.571 standard atmospheres. And we do the same thing here. 326 torr times the conversion factor, 1 standard atmosphere is equal to 760 torr. And we get 0.429. Atmospheres. Okay, so there is a very simple example that just illustrates how these partial pressures work. So this implies that every one of those types of molecules is independent of the other. And if you know the total pressure of the system of particles, and you know the concentration of one of those types of particles, you could compute the partial pressure of those particles. So let me erase this. For Avogadro's law, we have the following data. We got 156.5 of the total volume, which was this, cover up to here 156.5. The material vaporized, and then the pressure, the excess pressure was released to the pinhole. And at the end, what we have here is the number of molecules that fit on that container at the temperature that we are working, which is 368 Kelvin, that's 95 degrees Celsius, and the barometric pressure is there. So let's break what we got. We have a volume which is equal to 156.5 milliliters. We have a temperature which is, remember, is 95 plus 273, right? But we remember we're working in Kelvin, and that's 368. We have a pressure. And how you find the pressure? You check your cell phone for the weather report, and then you see what the barometric pressure is. And then the barometric pressure is not going to be in atmosphere standard. So what we got this day is 29.95 inches of mercury. So we got 29.95 inches of mercury. So step one will be to convert those inches of mercury into something that we know what to do with. So let's take that 29.95 inches of mercury, and if we take this inches of mercury and we cancel it, we cancel the inches by using a conversion factor. 1 inch is equal to 25.4 millimeters. So 29.95 is equal to like 761 millimeters. So we got 761 millimeters of mercury from inches of mercury, and this is called torr. So we have a 761 torr. That was the barometric pressure reading the day of the experiment. Now we need it in atmosphere. The ideal gas law requires atmospheres. Let's convert to atmospheres. We take this 761 torr and we convert it to atmosphere. 1 atmosphere is equal to 760 torr. And that will give us like 1.001 atmosphere. Next, what we do is we take the ideal gas law. Remember, the main objective of this experiment was to find the molar mass of the compound vaporized inside the container. To do that, we have to take the ideal gas law, So we write it here on the side, that's the ideal gas law. And we solve for n, the number of moles. Pressure over volume, and that's what you get. You get that the pressure volume product divided by RT is equal to n. If you do the algebra and you solve the ideal gas law for n, the number of moles, that's the information that you get from an experiment such as this. Now let's write that here. So we write pressure volume over RT, and the pressure is 1.001 atmospheres. The volume is 156.5 times 10 to the minus 3 liters. Remember, it's in liters, atmospheres. You had milliliters before, so we have to write this 10 to the minus 3 here. And then RT, 0.0821 liter atmospheres moles Kelvin. And the temperature is 368 Kelvin. From that we get our answer in moles. So we write 1.001 times 156.5 times 10 to the minus 3 liters divided by the product of 0.0821 times 368. And that's what you get, like 5.19 times 10 to the minus 3. So right here, 5.19 times 10 to the minus 3. And these are the number of moles of molecules inside that flask when everything vaporizes. Now, we use the definition of molar mass here. Is equal to grams divided by mole. That's what we're going to do here. We're going to take the grams. We got that there were 0.30 grams remaining after everything vaporized. And from the ideal gas law, we got that is 5.19 times 10 to the minus 3 moles. And that should give us an approximation of the molar mass of that compound. So 0.3 over 5.19 times 10 to the minus 3. And we get like, that's 57.80. 57.8. That's grams per mole. And then brave a little note, compare to acetone. And I think we got the, let me check to see if I have the molar mass of acetone, just to make sure. 57.9, almost, it's not that accurate, but okay. So we got like a 57.9, that would be exact. Okay, so that is Avogadro's law. Avogadro's law was mostly saying this. It says that if everything is kept constant, okay, this will be the constant part. Avogadro's law says, let's suppose everything here is a constant. Then the volume that you have is going to be defined by the number of particles in that container. So the number of particles determines the volume of the gas sample if everything else is kept constant. So you saw the pattern here. What we had was the ideal gas law, but there were sections of it. Charles took a look at volume and temperature. Gay-Lussac took a look at only pressure and temperature. Avogadro looked at volume and number of moles. And Boyle took a look at volume and pressure. And when all of those laws of observations were put together, because they were not available at the same time, it took like over 100 years for all this to come together. Then we got what is called the ideal gas law. And later, we got what is called the van der Waals equation, which takes into account some corrections that have to be made to the pressure and volume when the gas is not ideal. And that is mostly useful at high pressures and low temperatures. But when we're working with room temperature, normal pressures close to barometric, most of the gases are going to give the right answer. So that concludes our class for gas laws. And make sure you log into Blackboard, and if you have questions, please stop by during office hours. Have a good day, everyone.